Okay, so let's start. Where are we? Just to remind you, projects. You should be working on projects, even though most of you haven't received feedback from me, but you should work on it. Midterms, you got the midterms. In fact, most of you didn't go in to pick it up, which is surprising, but anyhow, it's over there. It's actually 3316 Don's office, and you should go and get it. The solutions are either out or will be out any minute, so look at the solutions, and hopefully you will learn from this too. Any questions on this? Okay, so where are we? So we started to talk about Bayesian learning. And basically, the key thing that we did is this. So we define a learning scenario. We used Bayes' rule, which is something that you've already known before. It's just different letters, H and D, where H is the hypothesis. Hypothesis could be many things, as we'll see today, but think about it as a function given the data, and we're looking for the maximum a posteriori hypothesis, and Bayes' rule says that the way to do it is to consider all hypotheses and figure out P of D given H times P of H. That's it. So that's basically everything there is. One simple issue is that often we will assume that we don't have any prior distribution, so P of HI is going to be the same, which means we're going to resort to maximum likelihood hypothesis. The maximum likelihood hypothesis is the argmax over all hypotheses of P of D given H. And the rest is just examples, you know, how to use it. And we've given several examples of how to use it, you know, some very simple, you know, 2 coins, and some a little bit more sophisticated, where you have continuous hypotheses, and then a few that, you know, have to do with a model of language, or some, this is the continuous case, or some document classification. The last example that we talked about is this one. It's another model of language, if you want, HMM or Markov model or hidden Markov models. And the game there was the following game. So we looked at this diagram as a way to generate characters, as opposed to the simpler model that we considered before. Here we have this notion of states, states that we call B, states that we call I, and we produce characters that are observed in the language either when we are in state B or when we are in state I, but with different probabilities. So when we are in B, we can produce A or B or C up to E with these probabilities. And when we are in I, we produce the characters with a different probability. So you could imagine the process something like this. You start with some state. The probability of the initial states are going to be other parameters of this model, in this case uniform I'm giving you. When you are in B, you produce a character, and then you move to another state, produce a character, and then you move to another state. Turns out that you stay in I, produce a character, and so on. So that's the sequence. And you can imagine, for example, that this is a reasonable model to assume part-of-speech tagging of sentences, right? So you can imagine that the way you produce a sentence, now each character would stand here for a word, and each hidden state would stand for the part-of-speech tag of a word. Noun, verb, adjective, determiner, and so on. So you could imagine that the way you produce a sentence is, first of all, you produce a part-of-speech tag. Maybe if you're at the beginning of the sentence, it's more likely that you'll produce a determiner than that you'll produce a noun. So you produce a determiner. Given the determiner, you produce a specific word. It's more likely that you produce a the or a then you'll produce table, because table is unlikely to be a determiner. And then you move to another state, maybe a noun state. Unlikely that you'll stay in, that you'll move again to a determiner state. Maybe you move to a noun, and then you produce a word, and so on. So this would be an example of a model like this. And the game is exactly the same game as before, right? So we have data. The data could be the x's, that is the observations that you see here, and the states. It could also be only the x's, and the states are hidden from you. This is when it's called hidden Markov model. We're going to talk a little bit about it maybe at the end today. But the game is exactly the same thing. You observe the data. If I give you this as data, it's relatively easy to compute P of xi given si, because you know which state you are in, and you're looking at all the observations that were produced in this state, and compute the statistics. The transition probability, P of si plus 1 given P of si, and the initial state. And once you do this, given an unlabeled example, for example, one question could be predict the S's. Okay, so you see an observation. No one tells you what states you're in, and you want to predict this. It's kind of like, given a sentence, predict the part-of-speech tag sequence of this. And it's the same exercise that we've done before, only that if you think about it in a simplistic way, this label, I'm calling this sequence of M states a label, is the argmax over all L, P of L given X. We know how to do it. It's P of X given L, P of L divided by P of X, just Bayes rule. The only issue is that these argmax could be difficult to compute, right? Because there's a lot of options there. Right? If you have a sequence of M states, even if each one of them is a Boolean state, you're going to have 2 to the M different labels here. So this argmax is going to be how to compute. We'll have to come up with a better algorithm maybe to compute it. But conceptually, the problem is solved, right? So it's basically applying Bayes rule. Questions? Okay, so I want to continue with this. And one question is how to use this Bayes formalism. There are multiple ways of using it because you can be Bayesian with respect to multiple things. For example, you could imagine that this capital H could be a collection of functions. But you could also imagine that it's a collection of predictions. And these two things will be different. Here's a simple example. So, okay, so just to write this down, if we are thinking about it as a function, basically language model is an example because we learn a model, and then we instantiate it and make predictions. We're just doing this. HMAP is this argmax. The second direction, when we look at specific prediction, is related to the it-in example that I started with last time. And really, you can think about this as an issue of thresholding, right? So you, rather than deciding which function you're going to choose, commit to it, and then use it to make predictions, you can say, well, there is a distribution over the functions. I'm not going to make a decision on which function to use. I'm just going to maintain this distribution. And given a data point, I'm going to choose the most likely prediction for this data point. So let's do this concrete. First start with example and then do it concretely. First of all, just to make sure that we understand that these things are different. So here is a simple case where I have a space of 3 hypotheses. And I computed the posterior distribution for these 3 hypotheses. Here it is. 0.4, 0.3, 0.3. So I'm going to choose H1. Right? This is the most likely hypothesis. And if that's what I'm doing, I'm committing to H1, it means that from now on I'm making predictions using H1. I don't question it again. So if you give me an instance, X, and it so happened that H1 of X is 1, I don't actually care what H2 and H3 say about X. I already know that I'm going to say 1. On the other hand, you could say, that I actually want to determine the most probable classification by combining the prediction of all the hypotheses and only then deciding. So I'm not going to commit here to H1, but rather I'm going to remember this distribution over my hypothesis space. In this case, I'm going to do the following thing. So I'm looking for the probability of the prediction given the data. Using the total probability formula, let's just make sure we understand. P of V given D is P of V given H and D, P of H given D. If you don't remember how to do it, hide this D for a second from everywhere. P of V, you know it's P of V given H times P of H, and then condition on D. So just a way to remember this. Now, notice that P of V given H and D is the same as P of V given H, right? If I know H, I don't need the data again. I already know that I need to compute P of V given H. So I can write it this way. And now this gives me the notion of a Bayes optimal classifier. So the chosen prediction is going to be the argmax over all possible prediction of P of Vj given D, which is the argmax over this sum over all hypotheses. Another way of saying it, I'm marginalizing over all hypotheses to choose the best prediction, right? So essentially, I'm taking the prediction of Hi, weight with a weight that is the posterior of Hi. This is what it comes out to be. In this specific example, the probability of 1 given the data is going to be P of 1 given Hi, P of Hi given D. The H1 said to say 1, and its weight was 0.4. 2 and 3 said to say 0 with these weights. So the weight of 1 is 0.4. The weight of 0, in a similar way, is going to be 0.6. I'm going to change my decision and predict 0 in this case. So again, it's different whether you commit ahead of time or you don't commit, but rather you marginalize over all hypotheses. It could be different. So it really is important what do you want to be Bayesian with respect to. Now, notice that computationally, doing this is much harder than doing the first one. Right? This is a very simple example. I had only 3 hypotheses. But in principle, I have to carry the distribution over H and every prediction do this marginalization, rather than just commit to an H and predict using it. Right? So that's different. Okay, so, but this notion is clear. Or questions? Okay, so the key example of doing or using a Bayes optimal classifier is that of the naive Bayes algorithm, which I'm going to move on to discuss now. So this is really a classifier, going back to talk about what we talked about earlier in the class, only that it's a different type of classifier because, as you'll see, we choose the prediction in a Bayesian way under our assumption. So this is our goal here. Just like before, we are after a function that maps instances x to V, which is our domain, a finite set of values. Instances are going to be described as a collection of features, x1 to xn. And given an example, we want to find out the most probable value in capital V, the most probable prediction. So again, we're going to use Bayes' rule in doing it, which means the maximum posteriori V is going to be the argmax over all V's of P of V given X. These are data. We know that we can write it. This is just writing down the X as X1 up to Xn. And now I'm going to use Bayes' rule. That means that it's argmax over P of the data given V, P of V divided by P of X. I'm omitting the denominator because it doesn't matter. It's the same for all V's, and that's what I get. So I got a prediction rule. And my job now is to estimate these from the data and do the prediction. Very straightforward. So notice that I'm using this convention. I'm sure you've seen it. When I say P of Y, I actually mean P of capital Y takes the value lowercase y. Okay, so how do we do it? So I want to be able to estimate these two terms, P of V and P of X given V from the data. Estimating P of V is very easy, right? So again, assuming binomial, as we assumed last time, for example, this could be one example. We'll see other examples, but in this case, all I need to do is count the number of times V appears in the training data. If I have two values, how many times you see positive example in the training data, how many times you see negative, and you got P of V. The question is, how can we estimate this, P of X given V? I claim here that it's not feasible to estimate it. What's the difficulty? I give you a lot of data, and I want you to estimate the probability of this data item, x1, x2, up to xn, given v. Let's say that v is yes. What would you do? Yeah? What do you mean? Okay, so the question here, or the attempt to answer is, we don't know if they are independent. But there's no notion of independence here. I'm just asking you to estimate this. What's the difficulty of estimating this? Just a data point, right? It's feature values. Yes?
So you have the training data labeled. So from that, you calculate.
I already used Bayes' rule, right? This is what I got after Bayes' rule. So how do I estimate this? Why can't I do the same thing as I did here? What was P of V? It's the number of examples that were yes divided by the total number of examples. I can do the same thing here. Yes?
If there's a lot of features, there's a lot of potential, I guess, assignments to all those features, and you'd have to have a lot of training data in order to find values for all of them.
So for example, let's assume that n is 100 here, and xi are Boolean features. Then my instance space is of size 2 to the 100. And what I want is to estimate the probability of 0011100011111. Right? A vector of 100 Boolean numbers. What's the probability that I would have seen it in my training data? Basically 0, right? So I will get that most of these probabilities are 0. So if I just want to go and estimate it from the data, unlike this, where basically I have two options, and I'm going to see enough examples to estimate these two probabilities. Here I have to estimate 2 to the 100 probabilities. Okay? That's the difficulty. And this is where independence is going to come in. I'll have to make some assumptions. But just written like this, without any assumptions, in any realistic case, I will not be able to estimate it. Okay? This is clear. This is really the key underlying assumption that we have to understand here. So we have to make some assumptions because most of these data items that I want to estimate here, most of these parameters are going to be 0 if we just look at it in a straightforward way. Okay, so in order to use the Bayesian classifier in practice, we need to make some assumptions. Otherwise, we won't be able to estimate these quantities. And naive Bayes is making very specific assumptions. Of course, you can develop a Bayesian classifier that makes other assumptions, but this is the most commonly used classifier in this domain. So what are the assumptions that we're going to make? So let's first write this down. I'm just writing down what I had before in a more explicit way. So I had this P of the feature vector given Vj. I can always write it as P of x1 given the rest of the features in Vj times P of the rest of the feature given Vj. That's always true. I'm just copying this here, and I'm doing the same thing for this guy. So I can always write it down as P of x2 given the rest and Vj times P of the rest given Vj. And again, I'm going to do this for each one of these last terms here. At the end, I'm going to get P of x1 given the rest and Vj, P of x2 given the rest and Vj, and so on, until P of xn given Vj. No assumption. This is just product rule, right? So now I'm going to bring an assumption. And the assumption I'm going to bring is that feature values are independent given the label, the target value. Okay? So it's conditional independent assumption. When I do this, I can say, well, P of x1 given everything and Vj is just P of x1 given Vj. It's independent of the rest of the features given Vj. Same thing here. P of x2 given everything, and Vj is P of x2 given Vj, and so on. So what I get is product of P of xi given Vj. So what does that mean? That means that now I have to estimate the probability of x1 being 0 or 1 given the label. That's much easier to estimate. P of x2 given being 0 or 1 given the label, and so on. So again, even if I don't have a lot of data, these parameters I can estimate. Of course, it's for a price, which is this assumption. Okay, so what is the model, the final model? I'm writing it more explicitly here. Under the assumption that the feature values are independent given the target value, I can write it this way. P of x1 being b1, x2 being b2, xn being bn, given v is vj, is just this product. Right? I actually wrote just this component. I did not include here the P of v. So really you can think about it as the following generative model. So we imagine, one second, that we generate the data this way. We first choose the label, Vj, according to this distribution, P of v, which means 0.6 v is equal yes, 0.4 v is equal no. And then given the specific v, for each v, I'm choosing the xi according to this distribution. So I have n numbers for each v. So altogether, I'm going to have, let's say in the Boolean case, 2 values here, and n values, n value for each one of them, so 2n plus 2 numbers. Question?
So are the features independent without given the target value?
Okay, excellent question. So I said my assumption is xi are independent given the label. And the question is, are they independent? What's the answer? Any suggestion? You can take a vote. Who says yes? Okay. I have a few votes. Who says no? Okay, most of you abstain, but by majority it's no. Which is the right answer? Actually, these two assumptions are completely different. And I'm going to give an example in a second. But let's just summarize what we have here. So in general, the learning method is to estimate these parameters. So size v parameters in order to get this. By the way, do I really have to estimate size v parameters? What's the minimal number of parameters I really need to estimate to get P of v? Size v minus 1, right? Because they have to sum to 1. And then n times size v for these guys, right? For each n, for each value here, I have n parameters. And again, it's really n minus 1. Because given that v is yes, I need n parameters, but they have to sum to 1. So n minus 1 will do. So that's the exercise. And how to estimate, you know already. You have to assume a model. Let's say assume binomial, and then you just count. But we've already seen at least one example where it's a little bit different. And you'll see more. Here is an important thing here. So far, you were used to learning as search, right? You were used to what I'm going to do is I'm going to be given a collection of training examples, and I'm going to try, and I'm going to search in my hypothesis space and correct myself in order to fit the data. Here, nothing like this happens, right? So I'm given the data, and I'm computing the hypothesis. That's it. Right? So it's really learning without even trying to achieve consistency, which is what we've tried before. Right? All the learning algorithms that we had, we tried to fit the data, minimize empirical error. Here, there's nothing. Right? We basically look at the data, compute something, and we got the hypothesis. So why does it work? Before, you kind of had intuition because you said, well, look at the training data. We're doing very well on the training data. We're going to probably do okay also on the test, modulo some assumptions that we actually proved with our learning theory. But there's nothing like this here, right? So here we just compute something. Why would you think it's going to work? Yeah?
Well, we know that if our assumption of how the data was generated fits the model that we've assigned to it, then we know that it will be the best model because we're following it.
Exactly. So here we made strong assumptions on how the data is generated. It's generated from a model with conditionally independent features. If that holds, what we've done is the best. It's going to work. Now, in practice, it's not going to hold, and we'll have to address the question of why does it really work? And there could be some answers that we'll get to later today. But in principle, it holds because the assumptions are strong assumptions, and if the data satisfies these assumptions, that's the best thing you can do. That's the best optimal classifier. Okay, so now we can answer your question about what are these assumptions. So we call these assumptions conditional independence, and you ask, is this independent? And no, it's not. In fact, it's not weaker nor stronger than this. It's just different. So I'm generating here two simple examples that show that these two assumptions are different. Yes?
So in practice, do we search in the different distributions? We don't assume one distribution from the beginning. We try distributions.
Okay. Typically, people don't do that. So there are two. So typical people assume a family of distributions, binomial, Gaussian, or others. I already gave a few examples, and just stick with that. What people do change is, despite the assumption of the distribution and the assumption, for example, in naive Bayes of the conditional independence, people actually change the features. I'm going to get to it in a few slides. But you're right. In principle, people could have tried different probability distributions, different parameterization of the data, and see what happens. Basically, see what. And sometimes people do this. For example, you could imagine under some conditions that you don't know the size of V here. This is when we get to EM. You don't know how many labels there could be. Will there be 2 or 3 or 5? And you can imagine, and these are different probability distribution. You can imagine searching over that. We're going to get to it.
And so it doesn't happen also that positive examples and negative examples?
This is okay here, right? So we allow that because notice that these parameters depend on V, right? So it could be, it will definitely be more interesting if you get different numbers given different V's here. So yeah, the distribution will be different in general given positive versus negative. Okay, so let's just think about the assumption. So what I'm giving here is two simple examples. I'm going to run through it that basically show that conditional independence and independence are different things. So here's the first example. I'm going to consider distribution over two Boolean features, x and y. The way I'm defining the distribution is basically as a Boolean function. The Boolean function is a conjunction between x and y. I'm constructing the following distribution. I'm constructing actually product distributions. So I'm assuming that P of x being 0 and being 1 is a half uniform. and the same for y. P of y being 0 is equal to P of y being 1 is a half. And then I'm generating a product distribution with these two, which means I'm basically assuming that in each quadrant here, okay, what happened? Okay. In each quadrant, I have a weight of 4, a fourth. Okay? Product distribution. So I kind of generate a distribution such that x and y are independent. I generate it such that the joint P of x comma y is P of x times P of y. By definition, independent. Now let's check the conditional independence. So I'm going to take L equals 0, the label being 0. Notice that L is 0 in 3 of these cells. Right? And therefore, P of x equal 1 given L equals 0. L equals 0 here. P of x given 1, it's a third. Right? Out of these 3 cells, in one of them, x is 1. And it's also equal to P of y being 1 given L0. Right? So it's this cell, a third. At the same time, P of x being 1 and y being 1 given L0 is 0, which means it's not conditionally independent, right? Because P of both of them being 1 given L equals 0 is not the product of this being 1 given L equals 0 times this being 1 given L equals 0. Example number 1. Example number 2 is going to show the other direction. So I'm going to take x and y that are conditionally independent, and I'm going to show that they are not independent. And again, it's a simple construction. I'm going to define the distribution in the following way. For L equals 0, I'm going to define it. X is going to be 1 given L equals 0 with probability 1, but y is going to be 1 given L equals 0 with probability 0. Inversely, when L equals 1, I'm going to define x to be 1 given this L to be 0, and y being 1 given this L to be 1. So this is the distribution, right? So you have here on this diagonal no weight, and here I have a half and a half. So I'm going to assume that the distribution of the label is uniform. And now let's compute it such that, now notice that this means that they are conditionally independent. Easy to check. Really, the product are going to be 0, which is what you want, and the diagonal is 0, so it's fine. So you can check this. And let's see what happens with the unconditional independence. So what do I have to do? I'm going to compute the probability of x being 1 and the probability of y being 1, and then the probability of both of them being 1, and I'm going to show you that it works. So P of x being 1 is P of x being 1 given L 0 times P of L being 0, plus given L equal 1 times P of L being 1. So notice that here you get 0.5 here times 0 plus 0.5 times 1. Sorry, 0.5 times 1 plus 0.5 times 0. So we get 0.5. And here is the other way around. So here we get, this is 0.5 times 0. And this is 0.5 times 1. So again, we get 0.5. But this probability, as you can see over there, is going to give us 0. So they are not conditionally independent. So basically, this exercise shows these two conditions are different. It's not that one is more general than the other. It's just different conditions. And whether it's a strong condition or not is something that you'll have to decide for yourself. But that's the assumption that we are making. Okay, and it's important to understand these assumptions. Okay, so now that we understand this, let's take an exercise with real data. You know this data already. It's the same data that we used for the decision trees. So we have these 14 examples, and we want to run naive Bayes. So what do we have to do? How do we estimate? We have to estimate P P of x given V, and that's really what we have to estimate, right? So P of V, and then P of xi given V, because we factored it using our conditional independence assumptions. So for the labels, we have two numbers that we have to estimate. And for each one of the coordinates, outlook could be sunny, overcast, rainy, given yes or no. So it's 6 numbers, right? 3 times 2. And as we said, really it's not 6 numbers, it's 4 numbers, right? Given yes, it's 2 numbers because the third one is just 1 minus the sum. And given no, same thing. So 6 numbers here, 6 numbers, 4 and 4. That's what we have to do. Now, we always have to compute all these numbers, even though in a given example, we're not going to use most of them. Because we're going to look at the observations and just choose those numbers that we need for this observation. Here is what we're going to do. So if you give me a new instance, sunny, cool, high, strong, I'm going to choose the appropriate numbers, but I'm going to do it for both columns because I don't know whether it's yes or no. So I'm going to do it from the yes column, choose the number for sunny here, the number for cool, the number for high, and for strong, and the same corresponding numbers from this column and compare the product. That's the algorithm. So these are the priors. P of yes is 9 over 14, P of no is 5 over 14, and these are the 4 corresponding numbers from each column. And you can go back to the table and check. And then the products gives me those numbers, which means I'm going to choose this guy. So one question here is, I have the probability of yes and the probability of no, and they don't sum to 1. Why don't they sum to 1? Typically, you would want to think that the probabilities of yes and no will sum to 1. What happens here? Think about this. Really, this is what I computed. Is this the probability that it will be yes? Or the probability it will be no? What's missing for this to be the probability? Actually, the probability of the data, right? Really, when we developed it, we had divide by the probability of x. But we took it out from the decision rule because we don't need it. So that's why it's not summing to 1, because I didn't divide by the probability of x. I don't need really to compute the probability of x because just normalizing is going to do it. The normalization factor is really the probability of x. So if you were doing this, you would see that they sum to 1. Okay, so that's one thing. Questions about the algorithm? Okay, so let's assume I'm changing the instance here, and the outlook is going to be overcast instead of sunny. So notice that for sunny, I got 2 over 9 for yes, and 3 over 5 for no. Remember, now I'm asking about outlook, so let's go back to the table. Now I'm asking about overcast. What will be the numbers for overcast? And consequently, what will be the prediction for overcast? Overcast. So I need to compute the probability of overcast given yes. 1, 2, 3, and 4 out of, I think, 9 yeses, right? What about given no? What's the probability of overcast, of outlook equal overcast given no? 0. What does that mean? What if I change this to overcast? what will my decision be? It will be yes, because the probability of this instance, when I change this to overcast, is going to be, given no, is going to be 0. It doesn't matter what the other values are. So what is the problem here? If I did not see one feature value in the presence of one of the labels, I will never predict that this has a positive probability, right? So even one feature that I've never observed given one label is going to eliminate the ability to predict positive probability for any instance that contains this feature value, right? That's a problem here, which is a very significant problem, hopefully you see, because there's a lot of data points, and it's likely that something like this would happen, that in the training I wouldn't have seen one feature value, and then it eliminates all examples that contain this feature value. So I need to do something, and the something to do is something that is called smoothing. So the standard way we're doing it, again, I'm assuming binomial assumption here, is the probability of something given v is the number of times this appears divided by the number. But sparsity is a big problem. And you could see two reasons for being sparse. One is that the denominator is very small. You didn't see a lot of examples. So all your estimates actually are not robust. That's one reason. And the second reason is that one of the coordinates is 0. One of the feature counts is 0. And that means it completely dominates the estimate. We will never predict that an example that contains this feature wins or has a positive probability. So we have to do something. And the something is smoothing. And there are many ways to smooth it. So basically what I have to do is I have to smooth the probabilities away from 0, or smooth the counts away from 0. As I said, there are many ways to do it, and it kind of depends a little bit on which probabilistic model you're working with. In naive Bayes, it turns out that it doesn't really matter how you smooth. All the methods amounts to doing the same. And the most common one is something that is called Laplace smoothing, that really amounts to this. So when I want to estimate the probability of xk given v, I'm estimating it. The original thing is going to be to do nk over n, where nk is the number of occurrence of the word or the feature in the presence of v, and n is the number of occurrence of the label v. So this would be my original estimate. And then I'm adding something to the denominator to push it away from 0, and the numerator to push it away from 0. And the something that I'm adding is m is the equivalent sample size, basically the number of labels, 2 in our case. And p is the prior of the estimate. If I'm assuming uniform, it's going to be 1 over the number of labels. Okay? So if I'm assuming here uniform, it's going to be 1 over number of labels times number of labels. So I'm going to have 1 here, and here I'm going to have number of labels. Specifically in our case here, when we have 2, I'm going to have nk plus 1 over n plus 2. And that's going to be, and that's called Laplace smoothing. And it's a relatively good way of smoothing. And there's been a lot of work on how to smooth. But in this case, everything really amounts to this. Now, this seems like a hack. It turns out that one can prove it. And the next slide is actually a technical proof for how to show it. And the interesting thing, I'm not going to go over all these details, but the interesting thing is that really it amounts to assuming a different prior, or a prior over the parameter. So what we're doing here is we are estimating parameters. How do we estimate parameters? Really what we did here is we just did simple counting. If you introduce a prior over the parameters, right, so we're going to estimate a number between 0 and 1. We want to be able to do it in the Bayesian way. We have to assume a prior. and then look at the data and compute the posterior. And if you do this, in one way, you actually get this. So essentially, I'm kind of going over this here and assuming, showing that this is going to be smoothed into k plus 1 over m plus 2. Right? So this is the Laplace rule. Instead of this simple counting, really the right way is to do this. Okay. So I want to move on to another important issue about naive Bayes. So far, what have we said? We said, here is data, and what we're going to do is we're going to look at the data, compute some numbers, and use it. No notion of consistency, and really the only justification we had was if the data satisfies the assumption, it's the right thing to do. So I want to question this in the next few minutes and try to get a better explanation, because the data is never going to satisfy these assumptions. I mean, data that you see is typically not conditionally independent. The features are typically not conditionally independent. Nevertheless, this algorithm is known to be very robust. So let's try to derive an explanation. So notice that so far, we did not look at it as predicting a function, a classifier, but rather as a prediction for a given point. You give me a point, I know how to predict it, right? So that's what we did here, right? You gave me this point, we computed some numbers and predicted. And then I changed this point, and we predicted. So it wasn't a function. What was the decision rule that we used in order to make this prediction? This is the decision rule, right? So we said we are comparing P of V being 1 times the product of xi given V being 1 with P of V being 0 times the product of xi given V being 0. If the ratio is greater than 1, we're going to predict 1. Otherwise, we're going to predict 0. Right? That's the rule. So I'm going to write it in a slightly different way. First, I'm going to introduce this notation. Pi is going to stand for the probability of xi being 1 given V being 1. Qi is the probability of xy being 1 given V being 0. Okay? So now I can write this as still the prior is here. And here I have a product, Pi. Now, I don't know which one to write. I don't know if it's going to be 0 or 1. The same trick that I discussed last time. So I'm going to write both of them. I'm going to write Pi and 1 minus Pi. But Pi is going to be written to the power of xi. 1 minus Pi is going to be written to the 1 minus xi. And I claim that this way of writing actually chooses whether it's Pi or 1 minus Pi. Let's check. So if xi is 1, what happens here? Xi is 1 means that I want this guy to be written, the Pi. And indeed, xi is 1, so I get Pi, and this disappears because it's equal to 1. Same thing if xi is 0. If xi is 0, I get 1 minus Pi, and this guy disappears. Okay? So it's a compact way of writing the right thing here, either the P or the 1 minus P. And the same thing appears in the denominator. Okay, so that's what I have so far. Now, I'm taking this guy, and I'm just writing outside 1 minus Pi. So I took 1 minus Pi in front of this expression. What do I get? So I get Pi to the xi, and I get 1 minus Pi to the minus xi. Right? Together, notice that what I have is 1 minus Pi to the 1 minus xi. Okay? So just algebra, same thing for the q's. And still, what I have here is a ratio, and the ratio is greater than 1 if and only if I'm saying 1. I'm predicting 1. So now I'm going to take a log, and still, I'm predicting 1 if and only if this ratio is greater than 1 is equivalent to saying that I'm predicting 1 if and only if the log of this is positive. So let's see, what does the log give me? It gives me log of these priors plus log of this ratio, sum over all the i's, plus now I have the xi, so I'm taking this in front, so I have xi times log of this ratio minus log of this ratio. Okay? And this has to be positive for me to say 1. So what do I get here? What does this look like? I said, now I have a decision rule. I'm going to predict 1 if and only if this function is positive. What does this look like? What kind of function is it? Well, you know what kind of function it is. If you have to choose one word to describe this function, what would you say? What kind of function is written here? Yeah? Suggestions? You've seen these functions before. Yeah? It's linear. It's a function that is linear in the xi, right? So what you have here is a coefficient and another coefficient. These are constants, right? And here you have a linear sum over numbers times xi, linear function in the xi's. So basically the decision rule of naive Bayes, which looked maybe magical before, really is a linear sum in the pi's and the qi's. So it's a linear function where the wi's are these, right? So it's log pi1 of pi minus log qi over 1. Or I can write it this way. So it's a linear function. It's not a general linear function. Well, at least it seems like it's not a general linear function because the coefficients are very specific and they're related to the data in a very specific way. You know, you estimate the pi's and the qi's by doing some counting, say, and then you plug it in, but you got a linear function. Now, from here, you can say two things. One, it's linear, and all the good things that we know about linear functions apply here. But you don't know if it's all the linear functions. That is, you don't know whether all coefficients are admissible, because it seems like here the coefficients are very specific, right? They are functions of some ratios of the data. In fact, it turns out, and you'll show it in the problem set, that it's not the general linear function. So there are linear functions that you cannot get using this. So naive Bayes, the class of functions that are the decision rules for naive Bayes are not all linear functions. But they are linear functions nevertheless, and this is really important. So basically, it gives us a little bit more confidence, I think, given that we know learning theory, that this is going to do the right thing, right? It's really low VC dimension functions, and it's going to be okay. So that's one important lesson. Let's do one other thing. Yes?
Can I go back one slide? How do you deal with the case that the denominator is 0?
Well, pi is 1.
For example, qi is 0 or pi is 1.
In the same way that I'm dealing with it in other learning algorithms. That basically means that I don't see some of the features, right? So in this case, it will never happen. I'm going to smooth everything away from 0, just as a simple answer, right? So I'll never have pi zeros and I'll never have pi's 1 or qi's because I'll smooth everything away from it. So that's an easy question. In practice, this is really what you're going to do, right? And not in practice, in theory, I'm going to eliminate this feature ahead of time because it's deterministic. So I'm not going to deal with it. Okay, so that's what we got, right? So we showed that the decision rule in the case of two classes is this linear function. I want to write it in a different way. So P of V being 1 given x is 1 minus P of V being 0 given x, right? You would all agree. that shows that I can write the probability of V, the label being 1 given the data, this way, as 1 over 1 plus E to the minus dot product. The algebra is here. You can follow the algebra. So basically, this guy is going to be my A, this guy is going to be my B, and I'm developing the algebra. So let's save this for a second. Believe that this algebra works. Follow it up. The interesting thing is that you've seen this before, right? So the probability in naive Bayes, when we use naive Bayes, the probability that the label is 1 over 1 plus E to the minus dot product, which is very similar to something that we've seen before. It's really the logistic function. And this actually is going to give us in a few minutes, the ability to generalize this algorithm in a very specific way and actually close the loop to the first part of the semester. So, and it's a very interesting thing. So really, these two together allow us to place these facts together, the linearity plus this allows us to place this theory of naive Bayes in a better way into what we've seen before in terms of learning theory. Okay, so what I have here in the next slides is a few more examples. I don't know if I'll get to it today. If not, we'll start with it next time. What I want to go to do now is dive a little bit down into why it works. So I asked the question, why does it work before? And the answer was, and it was the right answer, because you make assumptions. If the assumptions hold, it's going to be okay. But really, the assumptions are never going to hold, so we want a better explanation. So we started with, this is what we did in the last few slides. We showed that it's linear, and we showed that we can write it this way. So let's take the linear part first and try to use it. So essentially, I can look at naive Bayes in the following way. This is just a different way of plotting it, which is really a graphical model. We're going to talk about this more next week. You can think about this as a generative model. First of all, I'm generating the label. Given the label, I'm generating my features. Now, specifically here, I'm calling these features chi rather than xi, and the reason is that in practice, this could be the real features, or they could be some functions of the real features. You know, in real life, when you use learning algorithms, you don't always use the features, as we said many, many times. Sometimes you take simple functions of the features, let's say conjunctions of the features. So I can think about it this way. That's why I'm using kind of different notation. But what did we do? What is naive Bayes? Naive Bayes basically says estimate parameters. So we estimate parameters here, which is the probability of the label. What I'm writing here is the log probability of the label, which is look at all pairs x, j, j is the label, where L is 1, and divide by the size of the data set. That's the probability of the label being 1. And the same thing we're doing for each one of these edges here, right? So we compute the probability of the nth feature given the label, which essentially says, look at all the pairs x, j, such that the feature is on and the label is L, and divide by the number of pairs x, j, such that the label is L, right? This is just the simple statistics. So essentially, we collect these statistics, and then we make a prediction that is a function of these statistics, right? So the way we interact with the data is really, we don't really need to look at the data. All we need is some kind of an oracle that looks at the data and gives us some statistics. Think about it as putting all the data in a table, and underneath the table, just giving us these statistics, and that's it. That's all we need. We can throw the data away. We're making a very, very simple and narrow use of the data. This is a model that is called statistical queries, or linear statistical queries model, that doesn't really need the data, but rather needs just statistical properties of the data. The same thing, by the way, can happen with more expressive models. Look at HMM. I started today with the example of HMM. So in HMM, we have this notion of observations, and we have this notion of states. In this case, I'm denoting the states as t. This is t, this is ti minus 1. Ti plus 1, and the observations. And again, given the assumption of the HMM, the assumption of the HMM are that the probability of the observation, the ith observation given Ti, is the probability of the ith observation given x. Well, okay. And the important assumption is about the states. The Ti plus 1 state depends only on the Ti state. It doesn't care about the past. It cares only about one state. This is the Markovian assumption. Given this, you can, again, compute how do I estimate P of T. If I want to figure out, I know everything, and I just want to know what is the state here. You can figure out that predicting T really depends on these three probabilities. P of T given the previous state, P of the observation given T, and P of Ti plus 1 given T. Basically, you just look at this small blanket around T, and that's what you need to know. And again, you can write this just using simple statistics. I'm not going to, this type of statistics. You need to know, for when you look at two consecutive states, what is the first state among them? When you look at two consecutive states, what is the second among them? When you look at a state and an observation, what is the probability of this state? And you also, basically that's, these are the three numbers that you need. So again, the issue is that you need just to take these simple statistics, and the prediction is a linear function of these statistics, just like in naive Bayes. And this is the case for a lot of probabilistic models. In many respects, this takes kind of the myth out of these probabilistic models, because it tells you again, HMM is really a linear model. It's a linear model over pairs of states and pairs of states and observation. And you can do this, I showed it here for one state, predicting one state, but you can do the same if you want to maximize over many states. What does this mean? From a learning theory perspective, what we showed is that we care about the error over the training data. And if we have a simple model, low VC dimension, low expressivity model, doing well on the training data means that we're going to generalize well. And this actually could provide now a very good explanation also for why naive Bayes works, or why other probabilistic model work, even when the assumptions are not satisfied. And the reason is that if it so happens that we empirically fit the data well, learning theory says it's going to be okay. Now, you can still ask the question, why do you fit the data? We actually, our algorithm, the way we described it, doesn't even try to fit the data. It just looks at the data, computes something, and that's it. So in practice, really, it's not the case. In practice, the way people work is they will not work this way, but rather they will try to fit the data. They'll start with one set of features. If it's not going to work, they'll replace it with another set of features, measure the empirical error until they're satisfied with the empirical error, and then say, oh, now naive Bayes actually works. So really, people employ the standard learning theory convention and protocol even when they use naive Bayes. They don't just choose a model. This answers your question. They don't just choose a model once and that's it, but rather they change the model. Even though, if you think about it, if these original features were not independent given the label, definitely their functions will not be independent given the labels, right? I'm adding more dependencies. So I'm breaking the assumptions more and more. Nevertheless, I'm more expressive. So my chance of fitting the data is higher, and I'm basically playing the learning theory game. So that answers one question. There is one other question, and by the way, exactly the same thing happens when we devise more sophisticated models. We add edges to make the model more expressive so that it will fit the data. It still leaves one other hypothesis, one other question that I'm not going to answer in details. Basically, this is what I said now, right? So we really follow the learning theory protocol. We try to learn a hypothesis that actually is consistent or almost consistent with the data. And then we know that we're going to generalize because we work with simple models. OK, so there is one question, which is, why is it easy to feed the data with naive Bayes? It's not clear, because if you think about naive Bayes, it's really the following simple model. You think about writing all your data as rows in a matrix. Each feature is a column. And essentially, you take one statistics for each column, P of X given V, or maybe two statistics if you have Boolean V, two numbers. You eliminate the data. You just kept these n numbers, one for each feature. Why does this fit the data? I mean, why? It seems like it's really a product distribution assumption, and shouldn't be easy to feed the data. It turns out that you can actually show that product distributions are dense in the space of all distributions, which basically means, hand-wavingly, that for every distribution that you have over these n variables, pretty close to it, you will find a product distribution, which means that it's not going to be that hard to fit the data using a product distribution, which is a naive Bayes distribution. OK, so this kind of gives us one explanation. So this is the summary, right? So classifiers derived from probability density estimations really are linear functions, and it gives us an explanation. So if you think about what should I use there, should I use linear probabilistic assumptions, or probabilistic classifiers, or discriminative classifiers? The tension between these two is actually smaller than it was a few minutes ago, because we see that we can explain both of them in the same way. Probabilistic assumptions give us some advantage in the sense that the generative assumption is kind of appealing. You can think about what makes sense in your problem from a generative perspective. It makes sense that this is how data is generated, and this gives you an understanding, or allows you to put your understanding of the problem into your model. But in principle, it doesn't allow you to use very general expressive features, because the probabilistic model underlying them is going to be more complicated. But really, this shows that a lot of classifiers really can be viewed as linear classifier over an appropriate feature space, which is, again, an appealing conclusion, given that we have good theory for these kind of classifiers. OK, so two other things I want to finish with. We actually have two questions, given where we are now. So one question is, if probabilistic hypotheses are actually like other linear functions, does it mean that we can interpret the outcome of linear learning algorithms probabilistically? What we've done before, can we interpret it probabilistically? Question two, if probabilistic hypotheses are actually like other linear functions, can we actually train them in a similar way, discriminatively, rather than the way we trained it now, which is look at the data, do some counting, and derive the coefficients? The answer is going to be yes to both of these. And let's see why. So the first one, in fact, we already answered, right? So we already said before that, is that the first one? OK. That in the case of SVM, or all the algorithms, we can always write the decision, the probability of y being 1 given x, as 1 over this, where f was our linear function. The question is, what are a and b? So when we wrote it down, a was 1 and b was the b, the free coefficient. It turns out that you can play with a. You can tune a on your data, or on some set-aside data. And once you do this, you can show that you can tune it in such a way that what you will get is a probabilistic interpretation. That is, this thing will actually behave like a probability distribution. So that's an easy thing. And in fact, most packages that you'll use today. For example, if you use LBjava, it's already doing it. It's tuning it, and it's going to give you a number that you can assume behaves like a probability distribution. So that's the easy case. The second question is more interesting. If probabilistic hypotheses actually are like other functions, can I actually train them in a similar way? And the answer is yes, and it's called logistic regression. So basically what we said before in the naive Bayes model, we said, well, the probability of y being 1, let's say, given x and w is 1 over, this is the 1 over, 1 plus e to the dot product plus b. The dot product that we derive with the ratios of p's and q's. Now, in the naive Bayes model, we gave an algorithm to compute the w's. It was these ratios computation. But who says that I have to compute the w this way? I can just believe this and figure out what is the best w in a discriminative way. That is, I'm going to do something that is going to be more expressive. I'm not going to force the w, the coefficients that I showed you before, to be these ratios. I'm going to allow them to be whatever they want to be. And the way I'm going to do it is by discriminatively figure out what is the best w. This algorithm is going to be called logistic regression. Okay, we'll skip this for a second and just talk about it. So essentially, I want to optimize this. I want to find the w and the b that maximizes the log likelihood of the data, which is what naive Bayes did under the assumption of conditional independence. Now I'm going to just forget this assumption and just find the best w. So remember that we already did things like this, right? So we already asked the question, can I find the best WB that minimizes empirical loss? Right? Empirical loss is the sum over all examples of some loss function. Before, we called this SVM, and we call this perceptron. Now I'm going to call this logistic regression. Notice that the function that I'm optimizing here is slightly different. Typically, remember that what we do is we don't only minimize the empirical loss, we also add some regularization. So I'm going to add regularization here. We know what is good regularization in these cases, right? Something that is related to the size of W. And therefore, I have, just like before, a regularization term and an empirical loss term. And that's what I'm going to do. So in SVM, we minimized a very similar function where this was our loss function. I also commented that there is a L2 SVM that changes the loss function a little bit. It's a square root loss. And now we're going to do the same thing with this function. And if you look at it, you'll see that they are not that different. So this is the red curve, what we are having here. And the L1, L2 are the green and the blue curves. Very similar loss functions and very similar algorithms. Essentially, you're going to do gradient descent, or the basic algorithm is going to be do gradient descent on this loss function rather than what you did here, including in the exam, where you did gradient descent on this function. Very, very similar algorithm. So again, we kind of closed the loop. We started with a loss function that we showed is the loss function of naive Bayes, only that in the naive Bayes, we don't need to do optimization. We just know how to compute it. It's true under some assumptions. If you want to drop these assumptions and find really the best W, you have to do optimization. Okay, so let me stop here. There are a few other things to say. In summary, I'm going to go back to this summary next week, but I wanted to close the loop on what we've done here and in the previous part of the semester. Okay, have a nice weekend.
The question is, you explained the assumption of the conditional independence.